Okay, today we are going to learn about a reaction called the aldol reaction. And this is a really useful reaction because it is another carbon-carbon bond forming reaction. And it's a fascinating reaction, a little confusing at the beginning, but I think we can figure it out if we analyze it. If we take a molecule of an aldehyde, and one of the simpler aldehydes here, acetaldehyde, and react it with sodium hydroxide, we end up getting this. We end up getting this molecule that is 4 carbons long. So what we see here is we started out with something that was 2 carbons long and then ended up with something that's 4 carbons long. So obviously we have put those two pieces together. And if you take a look at it and say, well, I can see where this came from here. Here's if this is carbon number 1 and carbon number 2, then we have carbon 1 and 2 there, and you can see how that was an acetaldehyde molecule to begin with. And then this methyl group looks like a carbon 2 of the other acetaldehyde, and the CH looks like it's this CH that used to be a carbon double bond oxygen here, and now it's a carbon double bond carbon. So this reaction has put together two acetaldehyde molecules and formed a new carbon-carbon double bond there. And the overall molecule that it has formed here, the class of molecules, is that this is alpha beta unsaturated, meaning that it has a double bond between the alpha and the beta carbon, carbonyl, and more specifically it's a alpha beta unsaturated aldehyde, but we can also make alpha beta unsaturated ketones, as you will see here. So let's kind of let's try to figure out what's going on here. First of all, let's balance the equation, see what's going on. We have 2 carbons, and so if we have 2 moles to begin with, then it's taking 2 of these to make 1 of these. 4 carbons to begin with, 4 carbons in the product. 4 hydrogens to begin with, and 1, 2, 3, 4, 5, 6 hydrogens in the product. So we've lost 2 hydrogens here. 2 oxygens, 1 in each of these starting materials, and 1 oxygen in the product. So what we're missing here in this balancing of the equation is 2 hydrogens and an oxygen. And so we then we'll balance the equation with the only molecule we know that has 2 hydrogens and an oxygen, and that's water. So now we have a balanced equation, and we can, as we're trying to think through a mechanism, the next thing we can do is to figure out what bonds are broken and what bonds are formed. But let's list our bonds broken and formed. That tells you then, of course, what it is that you need to be doing in the overall mechanism that you're drawing. How are the bonds broken and formed, and in what order are they broken and formed? So we see we have a CO double bond, that there's 2 of those, and in the end we just have 1 of those, so we are breaking a CO double bond. And we are also forming a new CC double bond there. Okay, we have formed 2 OH bonds that we didn't have there before in forming water. So we're forming 2 OH bonds. And what are we breaking here? What do we not have in the product that we had in the reactant? We have 1, 2, 3, 4 CH bonds here, and we said we had a total of 1, 2, 3, 4, 5, 6 CH bonds in the product. So we had 2 of these molecules, which is 8 CH bonds, and now we are down to only 6 CH bonds. So we're breaking 2 CH bonds in the reaction as well. And if we look at carbon number 2 here, it has 3 hydrogens attached. Carbon 2 here only has 1 hydrogen attached, so we've actually lost 2 hydrogens off of that. So in the end, our mechanism that is a stepwise, how do we get from here to here, is going to have to include breaking the CO bond, forming a CC double bond, and breaking 2 CH bonds and forming 2 OH bonds. So let's think about what might happen. Here we have a base and we have acidic hydrogens. These are not particularly acidic, pKa approximately 17. So what will happen is that there will be some sort of equilibrium going on here. It's not going to completely deprotonate it, but some of these molecules will deprotonate. And so if we want to draw a mechanism here of this first step, we draw out the charges on the sodium hydroxide, and we can draw out one of these bonds to the alpha carbon there, and our base will come over, pull that off, dump the electrons onto here, and we have our enolate that forms. Okay, and so this enolate, as we know, then it has 2 resonance structures, and we can kind of get used to drawing these resonance structures where we're dumping in the electrons and dumping them up onto oxygen. So just a reminder of why this even forms at all. It spreads out that negative charge there. So we have an enolate here, which is, as we know, a good nucleophile because it's got that negative charge on it. Only some of these molecules up here are going to be converted. There's going to be an equilibrium there, and so we're creating a nucleophile in the presence of what? What is this originally? We've got an electrophile there. And so we have a nucleophile and an electrophile, and so if we then have one molecule of the electrophile that is still present in solution, run into a molecule of the nucleophile, then we have them reacting. So that happens. Let's write numbers here. 1, 2, 1, 2. And so here is our original nucleophile. The product of this is going to be the CH2 of carbon number 2 is now going to be connected to this carbon, which is carbon number 1. And we now have on carbon number 1 the hydrogen that's still there. We have now a single bond to oxygen. And we have then the methyl group still hanging off there. So this is what happens at the end of, this is what would happen if the nucleophile attacked the electrophile. So in the end, we are going to have to get rid of this oxygen here, make a double bond in here. And so we've got a strong base here. And so if we have the conjugate acid of our original sodium hydroxide there, that which would be water, that could protonate here. So in another step then, we can do a protonation with water. Remember, this is in basic solution, so we don't have H3O, but we have water. And we can draw that. And I'm going to draw out the hydrogens here on this alpha carbon. So what we have is a product here that is a neutral product, and we have a original aldehyde, and then on the beta carbon we have an alcohol or a hydroxy group. And so this original product is a beta hydroxy aldehyde. Or it is something that has an aldehyde functional group in it and an alcohol functional group. It is an aldol. Okay, so this is where the name of the reaction comes from, aldol reaction. It's forming originally an aldehyde and alcohol, and the alcohol is always on the beta carbon. So now what we have to do is to get rid of one more hydrogen here, and we have to get rid of this OH right here. Turns out the OH can come off as a hydroxide. It's not a very good leaving group, but if it's in a basic solution, then it can act as a leaving group. So in another, and at the same time, we can remove this hydrogen right here. So this is an alpha hydrogen, and we know that in equilibrium anyway, the hydroxide can pull off that alpha hydrogen. So if we pull off that alpha hydrogen, we can show this in one step. We're going to be using 3 arrows instead of our typical maximum of 2 arrows. But if this base here is pulling off the alpha hydrogen, if that pair of electrons comes in here and forms the double bond, then we're kicking out hydroxide. And again, not a good leaving group, but if it's in a hydroxide solution, then that's a reasonable thing to happen. And so if that does that, then what we're going to do is form water here, form a double bond here, and kick hydroxide back out into solution. So hydroxide is actually acting as a catalyst in the reaction that's being regenerated. So I'm drawing an arrow. This is our equilibrium arrow, but it's going all the way up here now to give you the final product, which is an alpha beta unsaturated carbonyl. So this is an aldol reaction, and every product of an aldol reaction in the end, after losing a molecule of water, is going to have a carbonyl and then a double bond between the alpha and beta carbons. Okay, we've looked at the most simple example of this, and we will move on in the next video to a more involved one.